Hello, I'm John Fitch. You know, the trouble with balloons is you never know just how much one of these will really take. Well, that's too bad, but balloons are cheap and you can always try another one. With satellites, it's different. They cost on the average about $50,000 a pound, and that's too much money to guess about. Before you put one of them into orbit, you want to know just exactly how good it really is. And that's the purpose of this laboratory.
Space Science 63 with John Fitch is a presentation of the National Aeronautics and Space Administration. Today's program, Tests for Success.
This is one of the test floors at the Goddard Space Flight Center in Greenbelt, Maryland. Here, most of our scientific satellites go through a rigorous series of pre-launch tests. And I'd like to have you meet Mr. John C. New, who's head of the Test and Evaluation Division. Mr. New, can you tell me just how much can you really find out about a satellite, how well it's going to behave before you put it into orbit?
Well, actually, we learn a lot about its performance here in this laboratory. We can recreate the conditions of the launch and of injecting the satellite into an orbit, and actually the conditions of outer space. We have facilities here, for example, that can recreate the conditions of vibration that you get during launch, of despinning when it's in orbit, getting into orbit, and the conditions of outer space.
Could we see some of these procedures?
Surely. Let's go down to our vibration laboratory and we can see the actual conditions being recreated there at that plant. During the launch of a satellite, there are two principal conditions that we're concerned with. One is the vibration that comes from the roar and noise as the booster lifts the satellite up into space. And the other one is the fact that the booster is beginning to acquire velocity. It's changing rapidly in motion, and this is acceleration.
I think I've heard our astronauts refer to both of these. I recall one of them mentioning how bumpy it was when he first got started, and of course also the being forced back into his couch as the rocket picked up speed.
Well, those are the effects of vibration and acceleration. Now, in this particular room here, we concern ourselves with the vibration effect. We have here a satellite. It's of the observatory class, one of our large classes of satellite. It's sitting on a vibrator, a machine which reproduces this motion, and it in turn is sitting on a large block of concrete. Now this block of concrete weighs 300,000 pounds.
See, and it's separated from the rest of the building?
That is true. It's separated from the rest of the building, and in fact it sits on some very large springs. These springs are of about the same size as are used underneath a boxcar on a railroad.
I see. You mean this vibrator would actually shake the rest of the building?
It would shake the entire building here, and of course would disturb some of the other tests that we're carrying out here. So we had to isolate it, and it's isolated the noise by means of this large room and so forth.
Does the vibrator move the satellite up and down a great deal, or very fast?
Well, the motion is not too much. Perhaps an inch is the maximum motion, but the rate at which it goes back and forth becomes quite rapid. It moves at the rate of maybe 5 times a second to as rapidly as 3,000 times a second. And this is, in fact, of course, the vibration effect. It's so fast, in fact, John, that one could not see it with the naked eye. We usually monitor these vibration tests by means of instruments and also by means of motion picture film, which we can slow down and actually look at a detailed part in the satellite and see its motion. Here we see a structural model of a satellite being vibration tested. You'll notice the motion in the lower platform and the movement of the particular component. Now we've jumped up to the next shelf.
What causes that?
Well, that's due to the different resonances that occur at different vibration levels. Here we see a satellite that gets a rocking mode due to this vibration. This is a detailed close-up of a particular satellite, and you can see that there's quite a bit of relative motion between the various structural members of the satellite system. We also have instrumentation of little accelerometers that measure these motions. This is a scene of a particular experiment, and you'll notice in this that the experiment actually fails, and there's quite a sudden change in the motion level as there it occurred. As I mentioned earlier, the other part of the launch phase environment is that of acceleration. Here we see a technician just completing the mounting of a satellite on this large centrifuge. This is a rotating arm about 20 feet in diameter. As it begins to move around, it will create the accelerating force similar to the launch vehicle going into space.
This acceleration is measured as so many G's, so many times the Earth's gravity?
That's correct. On this particular centrifuge, we can reproduce the equivalent of 50 G's. This is much higher than what the satellite would actually experience.
Well, now that we've tested the satellite for the problems that it faces in being launched, what's the next step?
Well, a spacecraft is spinning. When we take and launch it away from the second stage, it goes on a ballistic course, and to make it go on a straight line, we spin it up very fast.
Like a rifle bullet would?
Yes, that would be similar. Now, it's very important that the spacecraft be very accurately balanced during this operation. And that's what we're doing with this satellite that you see here. It's being checked for its balance. Now, actually, it's a little bit unbalanced, and we've determined by means of this machine the amount of unbalance. And we take a weight such as this, and actually we'll attach it to the satellite to see if this corrects that unbalance. So as soon as this stops, why, I'll show you how we take and attach this test weight. It's just applied to the satellite, as we see here. Then this will be spun up again and checked to verify that this is, in fact, the correct weight to correct the imbalance.
Now, that's very much like balancing an automobile tire, isn't it?
Yes, it's very, very similar to that. In fact, we actually use a lead weight here and attach that to the actual satellite that will be launched.
Now, does the satellite continue to spin when it's in orbit?
Well, actually not. We would want the satellite to be turning only very slowly there. So to do that, we have antennas that may have to come out, or weights. And this, when they come out, they slow down the satellite. Now, that's a little hard to show it on this machine, but I have some films of that, John. Why don't we look at those, and we can see that operation best from those films.
Good.
This is a sounding rocket which has previously been balanced. We see the cylindrical nose cone being kicked forward by means of springs. At the top of the spinning sounding rocket, we see the transmitting antennas that begin to erect suddenly.
They're just sort of thrown out there by centrifugal force.
That is correct. And in the center, we see a much longer transmitting antenna that's beginning to unwind.
With that long black cable?
Yes.
Well, with all of these tests, how is it possible that a satellite can ever fail once it's in orbit?
Well, of course, it depends upon how well we've done our homework, how well we've done our testing here in the laboratory. You know, we had a case of a sounding rocket that we were launching, and it failed, and this disturbed us quite a bit. We thought it might have been a random failure, but we shot another one, and it had the same kind of failure. Now, this made us come back here into the laboratory and look very closely at the test methods that we were using. And in fact, we found that this satellite, which sat on top of the rocket motor, did not in fact have a little centering button that was used in the actual launch. And we thought this might be giving us a problem, that when it was vibrated it would impact. So we changed it to exactly the way it was on the launch. And lo and behold, when we tested it in the laboratory that way, we got the same kind of failure that we had gotten out in the field. So we were very pleased in being able to find the cause of the failure, and we've launched several of those sounding rockets since then, and they've all been successes.
So not only do you test things here, but you're actually sort of testing out your tests.
This is correct. We conduct research ourselves into the test methods and the proper way of trying to recreate these conditions here in the laboratory. And unless we have tested them right, we know, of course, they won't necessarily be a success out in space.
Well, getting back to our story, now that we've got our satellite into orbit and the bearings are off and the antennas and solar paddles are out, is that about complete the conditions you have to simulate?
Oh, no. We're now approaching the most important part, and that's the space environment. Now, we have several chambers, space chambers, that we use for this. We've seen some small ones around the laboratory. Let's look at one of our medium-sized ones. I think the boys are putting a satellite into one now. Let's go upstairs and look at one of these now, John.
Now, can you actually simulate the environment out in space here?
Well, we attempt to do this to the extent that our technology will allow us to do it today. And this medium-sized chamber, which we see here, is an example of how we do that. The satellite itself is lowered down into place inside the chamber, and we have a large cover here which rolls forward and closes this chamber up and makes it absolutely pressure tight.
And then what do you do?
Well, we then have pumps on this chamber that begin to pump out all of the air that we have inside the chamber to create the vacuum condition of outer space.
Well, now, how good a vacuum can you actually create here on Earth?
Well, that's one of the real advances in the technology that has come from the space age. We used to think of vacuums in, just a few millimeters of mercury was very difficult. Today, in this chamber, we can produce a vacuum of 1 × 10⁻⁹ millimeters of mercury. Now that term may not mean much to you, but that's 1,000 billion, a change of 1,000 billion times, and that's very few molecules of air left inside the chamber.
Well, aside from the vacuum, what other conditions are there to recreate?
Well, we have in space the vacuum condition, which we've mentioned. We have the fact that it's very cold out in space. When you're not looking at the sun, the background is very cold. And we recreate this condition of coldness by means of what we call a shroud. And you'll see that around the walls of the chamber, the black area. And we have pipes into this material that we pump liquid nitrogen. Liquid nitrogen is at a temperature of 173 degrees below zero, measured on the centigrade scale. And that's very, very cold.
Well, now, you mentioned that sometimes it's in sunlight, and I suppose it would receive some heat from the sun.
Yes, the satellite, when it's in full view of the sun, receives a great deal of thermal energy from the sun. And we reproduce that, if it's just a question of heating it, sometimes by means of infrared lamps, like the heating lamps you use at home. But oftentimes we have to reproduce the actual wavelengths in the sun's energy, and this we do by special lamps called mercury xenon lamps, or a particular type that we're using here in our center.
Well, now, does the satellite simply sit inside of this chamber, or do you actually operate it?
Well, that's one of the interesting parts of this experiment that we conduct here. We actually operate the satellite the same way it'll operate out in space. We exercise its little radio, and we send it commands by means of the ground control equipment. And in fact, John, we actually have the same people who will control this satellite when it's being launched and gets out into orbit. Those same technicians are right here today actually operating this satellite just as though it were out in space.
So you're testing the people as well as the satellite.
That's correct. And we try to send them through a training program so they're trained to recognize the little idiosyncrasies, the peculiarities of each individual satellite. We don't build very many of them, just 1 or 2 or 3.
Now, can the satellite also send back its information from in here, the way
Yes.
it would in space?
We let the satellite operate, and it tells us what the satellite is doing and how it's performing. Also collect information about what the environment in the chamber is. And we collect all of this together, and by means of computers, which we can see in our computer control room, we actually take and operate the satellite so that we compare the data from the satellite and the data from the chamber. This prints out on an actual printed record so that the space scientist can see exactly how his satellite is performing and compare it with the expected conditions.
Well, now you mentioned that you have other space chambers in addition to this medium-sized one, I believe you called it.
Yes, this is about 12 feet in diameter, and we have some that go up to as large as 30 feet in diameter. Right over here we have our largest facility for checking out a satellite. It's called our dynamic test chamber.
Oh, what does that mean?
Well, we can test the mechanical motions, movements of those parts of a satellite which do in fact move out in space. It's a very large chamber, as you can see. It's some 30 feet in diameter and 60 feet tall.
Got to be able to put a pretty good-sized satellite in there.
Well, that's true. The lid closes by moving over the top of the vessel, and then we create in here rather mild conditions of vacuum. This chamber is large enough that a man can get inside of it and operate, and we have an airlock which permits the entry of a man.
Oh, can we go inside?
Yes, we can enter the airlock, and this permits a man to get inside the chamber. Of course, we have to set up many of our tests inside.
I was going to say you'd need to wear a spacesuit if you had to come in here when there was a vacuum.
Well, that's true, John. If there was a vacuum in here, a man would enter in a spacesuit.
Well, if you're primarily interested in checking out the mechanical parts, how it moves, then why do you need a vacuum in the first place?
Well, that's the interesting part about satellites. You see, a solar panel has a very large surface, and if we just moved it here in the Earth's atmosphere, there would be a great volume of air that we'd have to displace out in front of it. Or we take something like this material here. This is the material that will be used in the Echo balloon. Now, we're interested in the strength of this material and how much weight it'll support and how it will deploy or open up when we get it out in space. If we just check this here in the Earth's atmosphere with all the air, it would distort it quite a bit. So we remove all the air enough so that at least we get rid of the mechanical effects and then can check out the entire Echo system. Now, we of course couldn't see it in here right now, so we've taken some movies of this. Would you like to see some movies of this?
Very much.
All right. In this scene, you will see a section of the Echo balloon material unfolding. As the balloon material comes down from the top, you can see the small package on the bottom. This is being used to test the strength of the material. It's very light, flimsy material, as to whether it will adequately carry that instrumentation package. Right next to our large dynamic test chamber, we have its twin sister. We call it our space environment simulator. Now, it is of the second generation, a large chamber, big enough to handle our largest observatory class satellite. In it, we create all of the conditions of space, the vacuum, and the sun's energy, and the coldness of outer space.
Now, how good a vacuum can you get in this one?
Well, this one actually, we get down to the 10th scale. This is 10 times better than the one that we had seen earlier. We do that by means of various pumping systems. This is a diffusion pump, which we have here.
Well, how does that work?
Well, we use oil in this diffusion pump. This oil is heated up, and it's very hot down here. As that oil vapor rises, then it's condensed up at the top, and it falls back through a series of baffles, and this sucks the gas molecules out of the chamber, and they're carried on out through the vacuum line.
I gather you have more than one kind of pumping system.
Yes, we do. In addition to the diffusion pumps, we have mechanical type pumps. Let's move over to our control panel, and we can see the other types of pumping systems which we do use.
Do they all work at the same time, or?
No, they
separately?
actually work in series. We start off by the mechanical pumps. Let me kind of explain what we're looking at. This is a control panel for our entire chamber and pumping system. This is the chamber itself. These are the shrouds or curtain walls, which we had seen in an earlier chamber. These are our various pumping systems clustered around. Here is the diffusion pump, which we had seen earlier. Now, we really start out by first removing the bulk of the air by means of mechanical pumps of two types that we have here. After we get down to, maybe a millimeter of mercury or a little lower, we then turn on these diffusion pumps and they begin to capture the gas molecules, as I had explained. In addition, in this large system, we use another type of pumping system called a cryo-pumping system. We use a very cold gas, actually helium in this case. It's about 80 degrees colder than that liquid nitrogen I had talked about. And that is carried in a little panel off on the side. And as the gas molecule comes over here and strikes that panel, it's frozen, just as though you'd freeze water vapor. And this captures that gas molecule and does not allow it to go back into the system. We use altogether here about 18 diffusion pumps in pumping down such a large system. We have about 50,000 cubic feet that we're pumping down. We're not only removing the original air that's in the system, but also the gas that comes off of the satellite itself when it operates, you see, in the space environment.
Now, what about simulating the sun in this chamber?
Well, we can simulate the sun, and that's shown by means of this diagram here. We have a total of 127 lamps that shine down from the top. These are all arranged so they fit together. It's much like the honeycomb that you see in the beehive, you see. And this total area that we can cover here is about 20 feet in diameter.
You know, earlier I was wondering how a satellite could ever fail after it passed all these tests, but seeing all these various vacuums and heating systems and extreme cold, now I'm beginning to wonder how a satellite ever passes the test in the first place.
Well, that's a good question. Some of our experimenters have asked the same one. Actually, this business is quite different than what we ordinarily see in the American economy, where we're mass producing articles. In the space business, we're only producing one or two of a kind. And in satellite work, we build first what we call a prototype model. This is complete in every detail, and we test it to check out the design of that satellite system. And in fact, we tested about 50% more difficult and more extreme conditions than what the satellite itself will experience. But then, too, we never rely on just one system here. We try to put them in parallel where we can. So we build two flight units, the actual flight, one we expect to launch, and a backup in case something should go wrong. And we test both of those systems in full-scale testing here in this laboratory, as you've seen.
So you always fly one of these latter two systems?
This is generally the case. We actually had one satellite system, the Explorer 10, where we actually launched the prototype. It proved to be that good.
Well, what happens when something actually does go wrong inside of the chamber?
Well, this is a failure, and we, of course, have to fix that. We might go look at that now. In our failure analysis laboratory, we attempt to examine what has been the cause of a failure. As we found out in one of our chambers, the satellite was not working properly. It's now very important that we determine why it didn't operate properly. This means, in general, that we have to come in and diagnose in detail just what it was that failed to operate. Now, the satellite is made up of tens of thousands of parts. Some of them have as many as 15 or 20,000 parts. So it's quite a detective game to find out which part had failed. We very often can isolate this to a particular transmitter or a particular experiment that has not operated properly, and then from there we have to examine very closely, usually with a microscope, because we are building our satellites today out of very small parts.
So one tiny little part could jeopardize an entire project.
That's correct, and this could defeat the entire satellite. Now we see in this particular microscope here a very small tube. This is a sub-miniature tube that is used in the transmitter of this particular satellite. And we can see in the picture that the very fine grid wire that makes up a part of this tube actually failed during the vibration test. And this was what caused this particular transmitter to become inoperative. Now, in some of our other satellites and component parts, we are starting to use solid-state devices, things like transistors and diodes. And in this particular setup that we see next, we see a diode being examined, and in this picture, we see a very fine particle of dirt, which became lodged inside the glass capsule that makes up this component. And it was this very fine speck of dirt that caused this component to fail.
How did it get in there?
Well, this got in there during the manufacture of this device, and quality control is extremely important. Now, as we examine these parts, we find it's very important to keep clean and to be careful as we examine them, because often we can defeat the examination. In this next example, we see an entire circuit, a sub-miniature circuit, that is being examined, and we can see a hair here in this picture that has lodged onto this circuit and has caused it to fail. Once again, something during the manufacture of this particular circuit.
Well, it seems to me that the detective work you do in this laboratory must be a really important part of your entire testing procedure.
Well, it is. It's here that we find out the reasons that a part fails. It's here that we find out why a satellite might not work in space. But we correct each one of those and substitute a part that we know will work. And it's here that we move the satellites from the failure columns to the success columns, and we can say that every one that has gone through this program has been a success in space.
Well, thank you very much, Mr. New. We've been visiting the Test and Evaluation Division here at the Goddard Space Flight Center, where each satellite must meet and pass its test for success.